you see that it's actually climbing up the rod. This is very odd. So here's a nice still of someone using a proper motor rather than just me twisting it. And you can see it's gone up by quite a lot. This is a ruler, so this has gone up by an inch. And in fact, there are more dramatic pictures around where people can get this effect to go up by about 6 inches. So why does it climb up the rod? What overcomes inertia, which after all is trying to make the thing spread out like the water, so it's actually trying to dip in the middle? Well, again, remember this red stuff has got polymers in it. So here's my little polymers. They're sort of scrunched up in an equilibrium position. And now I start to turn the rod, which means I start to rotate all the fluid in the container. And as you rotate it, these polymer molecules get stretched out in the direction of flow. And as I said, they don't like being stretched. They want to relax back, and so they're now going to pull back along the streamline. So you've got some tension along the streamlines, which was there in the sliding plate flow, but the nice thing now, because this is a flow with curvature, is that that tension force now does something, because you see along here I've got an imbalance in the tension, so it's going to pull towards the center. So I get a force towards the center coming from the elasticity around that streamline. So it's rather like if you had a series of elastic bands along this was like an elastic band, it would pull the fluid in towards the center. So that's exactly what it does here. And it's that causes the thing to climb up the rod. Okay, so let's do some more fun things. So now we've got elasticity combined with this resistance to stretching. So now we can really have some fun. Okay. Let's try and get rid of this. So one thing you notice about this thing really is quite stringy, just like pizza cheese. And the stringiness of pizza cheese comes the same way. So this is just a syringe. So how many people have seen a siphon? You know what a siphon is? No. So if you want to get fluid out from one container into another, you can essentially suck it up through a tube and it'll flow from one container out of another. But here we don't need the tube. So what I'm going to do is I'm going to make this fluid flow uphill. So I've started off in the syringe, and then if you pull it up, you can see that it's actually still going uphill. Whoops. In case you couldn't see that, I've got another movie of that. Whoops. Sorry about this. Is that on me? Let's go Galari Rock. Okay, sorry, I'll go back to the beginning. Right. This is another version of the same thing. So here's the fluid being sucked up, and this is a slightly thinner fluid than the one I've got. And you can see you can actually get this one quite a long way. Flows. So any flow where you stretch these things out, you can really get some quite dramatic things to happen. And that's, of course, what you see in the pizza cheese. The pizza cheese, you have these long filaments of cheese that get stretched out. And, of course, it's that rubberiness that makes it hard to break. And again, it's associated with the fact that these polymer molecules in here are now getting stretched out. So stretching flows are actually more effective than shear flows at stretching these polymers out. And that gives rise, for example, to the Fano effect that I just showed you. But it also gives rise to this effect here, which I'm now going to attempt to demonstrate with the goopy red Gloop. Right. This one doesn't always work, I'll warn you. And that side. So as we said, this fluid's elastic, so we can pour it out and change our mind again. And then at some point it will actually start pouring. And it will, as you can see, it's still going, it's still pouring up front. And in fact now the only way to stop it is to cut it with a pair of scissors. And it recalls back into the container. This is a very famous picture of the same effect. Again, you can see you cut it with a pair of scissors, and the piece above it springs back into the container, literally as if it was a piece of elastic that's being cut. So I've shown you the, so this is another example of the Fano effect. Again, you can see it's still pouring, going up quite a long way to get out of that container. Okay, so where's the mathematics come into this? So what do I do, apart from playing with lots of toys? Which is a lot of fun, but obviously we can't do that as mathematicians, we actually have to write down some equations. So where's the basic idea of that? I'm not going to give you any equations, what I'm going to do is just draw you some pictures to show you where this is all going. So as I said, within these fluids you have these polymer molecules. You can think of these polymer molecules as strings. But they're strings that are moving around constantly. They're constantly reorienting themselves. And they get stretched out by the flow. Now that's a very complicated thing to model. I did show you a picture of some computer simulations of a single chain. But if we actually want to do a complicated calculation, that's actually far too difficult to put into a computer. So we need to simplify that idea. And we simplify it down to something rather crude, which is that we say that rather than, what's important here is the fact that this thing gets stretched out and that it can relax back. So we can think of this stretching out as being the effect of the fluid dragging on two ends of this dumbbell, and then we put a spring in the middle which represents the polymer pulling itself back together. And you can do quite a detailed calculation to show what this spring law ought to be based on the statistics of a random chain. And that's been done. Once you've got that, you can then work out a proper three-dimensional version of this stress. So you can measure the stress in the fluid, which after all is the force per unit area, generated by having a fluid full of these little dumbbells. And then you combine that with Newton's laws of motion to get yourself something that you can now calculate either analytically or more commonly using a computer. And this is just a final little calculation. There we go. Just to show how it springs. And you can see this one produces a nice thin filament with a little blob in the middle. And the colours on this simulation show you how stretched things are. So in this case, the stretch is all happening in these thin filaments here. Okay. That's it. Thank you very much.